Uh-oh. What did I do? The 105. Okay, yeah, that's correct. Why isn't this up there now? All right, good. I hope that's working. Very nice. Hi, how are you? What's your name?
I'm Amy.
Amy, very good. What do you do? Have you started your research yet?
No, I'm still finishing my BS degree, actually,
Nice.
so I'm in the accelerated.
Good, welcome. Glad to have undergrads here too. I saw there was a few. Good, great. Lead, action. Nice. Excuse me. Okay. Question is, how do we get the students so that they have access? Okay, so great. Right. Welcome. Very good. What's your name? I met you on the pizza thing, right?
Yeah, Veronica.
Veronica, very good. And you're working with who?
I'm working with Dr.
Very good. Very nice. How about you? What's your name?
Tyler.
Tyler. Very nice. Nice to meet you.
Good to meet you.
Good. Are you doing your research yet?
Yeah, I'm in my third year actually.
Oh, nice.
Direct PhD.
Oh, great. Very good. Welcome. Hopefully, my goodness. What the heck? That's kind of annoying. Oh, man. Where's the computer? You just see the, when you zoom in, do you know how to, if you close the corner? Yeah, just see if the Zoom is up and running. The other thing I should probably get the course webpage opened. Oh man, I should have thought of that. App Store.
Yeah, I can see it.
You can? Good.
Yeah.
Thank you. Oh, it's got you on there though. Oh, maybe because you're talking, it switches. You have a question, right? All right, let me get the. Great. Okay, let's see. Okay, great. All right, I guess it's 9:30, so welcome everybody to ECE 5105. Yeah, 5105, electromagnetic waves. I'm super excited to teach this course, and I hope you guys are also super excited to be here. I think by the end of this sequence, if you take the next course as well, very confident that you'll be experts in electromagnetic theory, right? Which is something very useful for the degree of electrical engineering. It's founded on the 4 equations that we're gonna master over the following semester. Even if you don't take the next one, this is a very good, this is the classical electromagnetic theory plus some advanced topics. I've tried to sprinkle into the lecture a lot of things that I've been doing throughout my research that I found useful. And I also think that You'll see some topics, maybe not too many, that you might know of already, but it's great to see things from another perspective. I even myself still read undergraduate texts in electromagnetic theory a lot because it's great to see things from a new, fresh perspective, some way of explaining it that might turn on a light bulb differently than you had understood it before. So I'm glad to see the turnout. We have a lot of students here, 24, which is more than this class normally has. So first thing I want to do is bring up the Canvas page. Everything that's going to happen in the course is through this page. I think you guys are all familiar with this. So we have the syllabus here that you can get to from this link. The lectures are Tuesday and Thursday, 9 to 10:45, 9:30 to 10:45. There's office hours in my office from 11:30 to 12:30 on Tuesday following this class. So a little bit of a break between the end of the course and the start of the office hour for everyone to migrate or make like a wave and propagate over to that building. And then we have the office hour Zoom link. If you want, you can join by Zoom. I'll have my Zoom open during the office hours because we do have a remote section as well. Then the lecture recordings. Every day the lecture will be recorded. You can find the recordings on the course gallery page, which I don't know if my view is the same as yours, but if you look down here, there's a link called course gallery at the bottom, and it should have the recordings for every lecture. Okay, and then there's the live Zoom class link that you can click to join the class live. Here's a schedule that we have, but rather than going through that, I'm going to open up the syllabus because this thing's kind of okay. So here's the syllabus for the course, right? Some of the repeated information. You can join the class remotely. I prefer you guys to be in the class physically. You'll get much more out of it. We'll engage more. We'll have more, face-to-face interaction. But if you have to, let me know that you can't make it, and I can arrange things for you to join. Even if you're here at Blacksburg, you can join remotely. So these course objectives are kind of outdated. They're directly from the course catalog, which I'm going to update soon. I'm going to be in part of this committee that's going to try to update these objectives and the description. But you can read them. They're here. We're going to learn everything in a book called Advanced Electromagnetic Theory or Advanced Electromagnetic Engineering, which is a good book. It's the one I learned from. Here it is. Advanced Engineering Electromagnetics. They're at their second edition. I believe there's a third edition coming out. Everyone needs to buy the book or find it online or whatever you need to do. But you need the book because part of the homeworks are going to be to read the book, right? And the way I've structured the course, you're really going to start to understand this stuff, which is very, very useful for you and your studies. There's another book called, I think it's called, oh, I didn't put the title here, which I should have. It's called Applied Electromagnetic Theory. Gosh. Applied Electromagnetic Theory. It's a free book. It has very similar content. You can get it from the website. You can get it from the website. Well, you know what I think is happening? If I walk here, does it switch? No, okay. Yeah, this book is a supplemental text, right? It's not going to be our main text. We're not going to read directly from it. There won't be any assignments out of it, but it's a good book to have for extra information. Homework, there will be approximately 7 homework sets, and each one will be penalized 20% for each day that you turn it in late. So try to get your homework in on time, right? There's 1 midterm and 1 final exam. So the final exam's on the scheduled date. The midterm is on Tuesday, October 17th. It's an in-class exam. For those of you who are joining remotely, we'll work it out later, but I think my plan is to have some kind of camera on the desk so we can see that you have an empty desk in front of you. And we'll be watching the monitors. Okay, great. So the grading is the weighted average of the homework, 50%. We have a 25% midterm, and a final exam is 25% of your grade. So if you do well on the homeworks and you do reasonably well on the exams, you should be okay. All right, so the way that the course is going to be graded is direct on points, right? That way you know where you stand the whole time. There's no, this might happen at the end of the course, it might curve it or whatever. If everybody's low though, and the average is like C or something, then I might shift everybody up. Everyone will get the same amount of points added. So it only help everybody the same. But anyway, you have 7 homeworks. Sum up the homeworks, the score you get, and you multiply it by this formula here, the midterm and the final, you'll get exactly where you are in the course. So I do understand that on straight points, it might be difficult thing. You might be worried if you mess up one exam. If you do bomb one exam, see me. I'll set up some kind of extra credit for work for you. So you don't have to be super scared about that, right? Okay, but there's no curve. It's going to be straight added to everybody to get everybody the average. All right, good. Now, this university doesn't implement it, but what I like to do is get some feedback from you guys about mid-semester in order to adjust the course, right? What's working, what isn't? Do you guys want to see more problems solved? Are the lectures too fast? All kinds of things that you can complain or even reinforce. So in mid-semester, I'll give you a survey that I make. And to give you incentive to fill it out, you can get 3% extra on your midterm grade. So if you got like a 83, then you would get an 86. You get 3% extra on your midterm if you do the survey and return it to me. And what I do, if you've taken a class with me before, I always implement things that you tell me at mid-semester. So the course will change mid-semester to the end, the second half, based on these mid-semester instructor reviews. Okay, honor code, please everybody read it. There's some new additions to this based on ChatGPT and Chegg and Course Hero, all of that. Just follow this, right? Okay. And ADA accommodations, if you have those, see me and I can accommodate. Okay, last thing is this copyright. So these lecture notes I created, they're from, I spent a lot of time on them. They're for you guys, so keep them for your own reference. Don't go and post them online or anything because some things in the, I've done my best to make sure we haven't used any images for copyright or anything, but just in case, that wouldn't be good, right? So keep them to yourselves is all I'm saying. Don't redistribute them. Okay, topics. First thing we're gonna do is go into a course overview, which we're doing now. Then we have an electromagnetics review, so we're all on the same page. We're gonna review the fundamentals of electromagnetic theory, starting from the derivation, or maybe not derivation, but the statement of Maxwell's equations. We're gonna look at constitutive relations, boundary conditions, power and energy, time harmonic fields, generalized coordinates, which is a super useful thing for you guys, which is how to do divergence, curl, gradient in any coordinate system. So you'll be able to derive that. Of course, in the back of the book, you have it for rectangular, cylindrical, and spherical, but what if you're presented with a particular geometry, which might happen, and I'll show you examples when that does, where a different coordinate system would make the problem much easier to solve. In that case, how do you do integration? How do you take the curl of a vector field in some kind of elliptical coordinate system, for example? And you'll have a framework and a way to do that. Then I'm a metamaterials guy and metasurfaces, so we're going to dig deep into electrical properties of matter. We're going to learn about dielectrics, the origin of polarization and permittivity. We're going to do the same thing for magnetic material. We're going to look at dispersion. And we're going to then get into losses, complex permittivity, permeability. This will be a fun lecture. I think you guys will really enjoy that and start to get a visceral feel for the interaction of light and matter. Then we're going to get deep into wave equation and solutions in the three most common coordinate systems, right? Cylindrical, spherical, and Cartesian. And then we'll also solve the wave equation in generalized coordinates, allowing us to reuse the concepts that we had developed in the generalized coordinates lecture. We're now going to be able to separate the wave equation through separation of variables in whatever coordinate system admits it, right? And we're going to do that in sort of an elliptic coordinate system. So that's pretty useful. Then we're getting into propagation, polarization. We'll look at TEM modes for plane waves and uniform plane waves. And then polarization, that's going to be a fun lecture as well. And reflection, transmission. So these are the kind of concepts that you may or may not seen, but now we're going to look at multiple interfaces, reflection, transmission into lossy media, and oblique and normal incidents. And we're really going to understand, we're going to take this to a complete understanding, right? Why is reflection coefficient as it is and so forth. Then we're going to start to solve radiation problems, right? The whole idea of this is if we're given a source, how do we calculate the electric and magnetic field? That's the definition of solving Maxwell's equations. It's a pair of differential equations that you have to solve together that are for the electric and magnetic field. So if you solve that set of differential equations, what you've done is you specified the electric and magnetic field everywhere in space, right? If you give me a point in space, x, y, z coordinates, I give you the vector there, and I can do that for all such points, and that vector represents the electric force, the electric field, or the magnetic field, right? And you've specified in all space, which is a pretty powerful solution. But we're going to solve that problem under the the assumption that we have an arbitrary source distribution. We want to find the radiated electromagnetic field from that. And we do that through what's called vector potentials. It's a very powerful approach. And we will solve the inhomogeneous vector potential wave equation. That's going to be a fun lecture as well. And then we're going to get into really the heart of really solving more complex problems in electromagnetic theory, theorems and principles. If you master the theorems and principles, then you'll be well equipped to solve problems that aren't directly straightforward, right, or canonical. It's these theorems and principles that you are, when you get really well at applying them and understanding them, that you can solve a much wider class of problems that are much more difficult. And the good thing about electromagnetic theory is it's well developed, and you can have or you can develop models, right? Mathematical models. Nothing's better than having a mathematical model that models physical space, right? Or physical phenomena. So if I'm able to vary a parameter, I can watch the dynamics unfold because the model tells me what's going to happen, right? So nothing's better than having that, and using these theorems and principles helps you develop more powerful models for problems that you're going to solve. And then I guess the heart or the big conclusion of this class is scattering, right? We have a plane wave coming in. We have some kind of source exciting some geometry. This is going to be, I might have to order a new one of these. Okay, so I have some plane wave, some excitation, some arbitrary geometry, and I want to calculate what the scattered field is, right? Scattering. Antennas are scattering devices if you feed them, right? You could have RCS, radar calculations, things like that. A lot of problems in electromagnetics deal with scattering. So you're going to become an expert at scattering. Then, when we have time, which we should, I'll give a lecture on metamaterials and metasurfaces. So this is TBA for now because I'm still developing that lecture, but we'll get some time for some fun things at the end of the course. But you guys will be well equipped to understand all of these concepts and the models that are developed to design materials and surfaces that interact with electromagnetic waves in such a way that you can completely control the wavefront, polarization, amplitude, phase, and so forth. All right, so here's the schedule really quick. Let's get through this. Today is the 22nd. This is lecture 1. If you look through here, this index here, if you will, it's the lecture 1, session 1. So the lectures that I upload, there's like 9 of them, right? 1 for each of these chapters. We'll have 1, 2, 3 sessions for each. Hopefully we can move fast enough to do that, right? And remember, if you're going too fast, interrupt me. That's another thing. This class super informal. Just interrupt me. You don't have to raise your hand or anything, all right? I don't take offense. I'd rather open up discussion, right? And if you don't understand something, or if I'm going too fast, then you should do it by all means. Interrupt me and say, I don't understand this, I don't understand that. You get the most out of it when you follow along everything, right? Okay, so I want to bring your attention to the following. This week, I will be away at a conference. And there's no class, it's canceled on this date, so you don't have to show up. And this one, I will pre-record for you. You can watch it at your convenience, or you can come here on that date and the room will be empty, and you can play it here if you want. But it'll be uploaded. I'm going to record it on this Friday, so I know exactly where we're at. And then it'll be uploaded by the time you need to watch it. All right? Nothing else is surprising in the schedule. And there's homeworks. There's homework, the due dates for the homeworks. They will be assigned at least a week ahead of when they're due. But all the due dates are there. So there's no surprises. You know exactly what you need to do and when, right? Thanksgiving break. And then we have the end of classes and the final exam. All right? Any questions on the schedule, expectations, grading? All right, let's get into the fun stuff then. Very good. So let's hope that this. All right, so welcome to ECE 5105, electromagnetic waves. We're going to learn all about the classical electromagnetic theory and become experts in the advanced topics as such. All right? So a quick about me, where did I come from? I came from California, SoCal, born and raised, got my doctorate at UCLA, went to Michigan to do a postdoc, packed up everything in a little truck and drove me and my dog there. Did a postdoc through the pandemic, and then I finally got hired when the hiring freezes were kind of lifted. And now I'm here at Virginia Tech with you fine people. These places I used to work at for a little while. So I did some amplifier tuning and stuff. I worked at NASA and this avionics company. Okay, the course, 27 lectures, 1 midterm, 1 final. This is the book. This is the one I learned from. So I've read it cover to cover, and you guys should probably get nearly cover to cover reading it if you take this in the next course. There's a second edition that looks like this. It's a lot thicker than this one, so it's more intimidating. I'm biased to this one because that's the only book. If I got rid of every book that I had on my shelf and I only had one to keep, it would be that one. It's like a reference Bible, you know? And then here's the other book from Sarah Bondi. This is a free book. It's got a lot of the same material in here. So you can get away with it if you want, but this is going to be your best friend for your career. So buy this book. I recommend it. And buy the physical one. It's good to have it. It's like some kind of trophy. You know, you read it. You know all the information in it.
So the first edition would be good for the.
Well, okay, so this one has more stuff in it, right? He's added stuff into this new edition, but it's like that thick, and you got to carry it around. And this one's much thinner. It's like that, and most of it's the same. Everything we're going to learn is in here, right? And if you need extra topics in here, you can obviously, if you buy it, you might get some cheaper, right? Because it's an older edition. I like the black one. Okay, good. So here's some memes. These I had from my undergraduates, but you guys are going to understand this now. All right. Okay. So references. One last thing. Let me go here. In the process of creating these slides, I always put this disclaimer. I've used figures from the textbook for the course and everything. So the reason I put this up is if you're going to see a lot of animations, a lot of figures. I tried to make this stuff come to life instead of just having equations and words on the slides. I tried to make a lot of videos, animations, GIFs, and things. So I pulled a lot from the internet. So if there's anything, not to you guys, but if anyone, okay, so I put that on the bottom of beginning of every lecture. Okay, so first thing, we're gonna start basic. We're gonna build up fast. We have coordinate systems, rectangular, circular, cylindrical, and spherical. In the rectangular coordinate system, each point is defined by 3 real values. You define the X, Y, and Z coordinates. In the circular cylindrical system, we introduce one angle and keep 2 lengths, right? 2 coordinates and 1 angle. And by introducing that angle, you're going to complicate the divergence and the curl operations. And then finally, in spherical coordinates, we introduce 2 angles and keep only 1 length, right? The radius. We have theta and phi. Hopefully, you guys have all seen these before. You're going to become very proficient in using them. Rectangular is obviously the easiest coordinate system. We also like circular, cylindrical, and electromagnetic theory because a lot of problems involve cylindrical symmetry, like line sources or cylinders or coaxial cables. So it becomes very useful. And spherical coordinate system is also very useful in antenna engineering and electromagnetic theory because anytime you're far away from the source, say you go infinitely far away from the source, no matter how big that source is, right? Could be the size of the Empire State Building. If I go infinitely far away from it, it looks like a point. And we're going to be in what's called the far field, where every radiator kind of is best described with angular variables, theta and phi. All right. Now, also, you can define vectors in these coordinate systems, unit vectors, X, Y, and Z hat. And these unit vectors are constant. They don't change with position in this coordinate system. That will simplify vector calculus operations in this coordinate system. We have circular cylindrical, where we have these 3 unit vectors, which are rho, phi, and z. And as you can see, so remember what a vector is described by 2 properties. It's magnitude and its direction, right? So if a vector A is equal to another vector B, then they must have those 2 properties in common. One vector could be here and one could be way over there. But if they have the same length and the same direction, then there's the same vector, they're equal. So this vector here, rho hat, say x hat. If I translate x hat or my point P to any other place in space, x hat has the same direction, same magnitude. It's a unit vector. But rho hat now, if I change to another position P, so I'm the z-axis, this is rho hat's changing direction. Oh, man, okay. I gotta buy a new one of these. Rho hat is changing direction. Okay, rho hat changes direction, right? Same length, it's a unit vector, but it changes direction. So it's a function of position. If you differentiate that unit vector, you're gonna get some value, it won't be 0, which you guys will do in your homework. Spherical coordinate system, you have r, theta, and phi, and you can develop differential lengths, differential surface areas, and differential volumes in these coordinate systems. All right? We got to become very good at vector calculus because Maxwell's equations are written in the framework of vector calculus, and they're most easily described in terms of curl, divergence, and so forth. We're going to understand these operations. We need to become proficient in vector calculus. So the first lecture, we're gonna do a little review on vector calculus and Maxwell's equations. So what does it mean to take the derivative of a vector, right? If I have a vector quantity here, I wonder if the online students can see me point to that. Maybe I'll write instead. So if you have a vector here, R, this is the vector here, and I want to differentiate that vector. Say that vector is a position vector, meaning that it's parameterized in such a way that the variable t allows a path to be traced by the tip of the electric of that position vector rather. So as I increment t from some interval a to b, this vector has different coordinates, right? Its coordinates, its components rather, are a function of the parameterization variable t. At some t, I have this x, this y, and this z. At some other t, this vector now has this x and this y and this z. So the vector is a different length and it points to a different position in space. So at every t, this vector is pointing to a different position in space. And if you follow the tip of that vector, what you end up doing is tracing out a path. So if I want to differentiate that position vector, what do? Well, I use the exact definition that I know of from differential calculus. If I take the limit as delta t goes to 0, and I evaluate that vector at r of t plus delta t, and I subtract r of t and divide by delta t, then what do I get? All right. So here is r of t plus delta t. If I subtract these two vectors, then I get this vector here, and that's a tangent vector to the curve. All right. So the derivative of a position vector, or the vector derivative, is a tangent to the curve, right? That'll become very useful. All right. Then we can also do flux integrals. So a flux integral is what I want to do with a flux integral. I have some vector field here that exists all throughout space, right? At every single point, x, y, and z, I can define a vector. And I can do that for all such points. So this is a representation of that vector field in an uncluttered plot of a representative few number of vectors. If I want to find the flux of that vector field through some surface, here's an open surface S. That vector field is penetrating that surface. It's like I have maybe a sheet, right? Some kind of sheet, and I have a flashlight that's shining through it. Then what is the amount of light that goes through that sheet, right? This is what's called a flux integral. I take the vector derivative, or sorry, not the vector derivative. I take the vector field F and I dot it with a ds. What is ds? ds is a unit vector that represents the differential surface area, but it's directed. So I have a dx dy, but then I also have a normal vector to the surface that allows me to do the integration. So it's a vector area, right? Differential area. I take the derivative or the dot product of f and ds and I add that up everywhere. So we'll do that plenty of times in this course. You can do that over a closed surface as well. So if I have a source inside, like a light bulb, and I cover it with a whole sheet, closed sheet, I want to find out what all the light is that comes out of it. Okay. So Maxwell's equations, you must have seen this before, but we're going to become experts. We have 4 laws. We'll find out why there are 4 shortly. There's Gauss's electric law, the divergence of D equal to rho. So I hope at this point, when you look at this, you've seen it, but you don't have a real strong feeling of what these represent exactly. And if you do, that's even better. But I hope that that some of these things, you can't read these symbols like you would read text off of a page and see dynamics, because by the end of the course, you will. So I'm excited to see that happen for you. So Gauss's electric law, divergence of D equal to rho. So we'll describe these quantities on the next slide. Magnetic law, divergence of B equal to 0. Faraday's law, the curl of E is minus partial B partial T. And then we have Ampère's law, which is the curl of H equal to J plus partial D partial T. So one thing I want to mention is these script letters. Whenever you have script letters, you have vector fields, which are a function of time as well as space, right? So these vector fields, for example, E, script E rather, is a function of X, Y, and Z. So you give me an X, Y, Z point in space. I give you a vector at that point, but also a function of time. So at that point, you give me an X, Y, Z. Here's this X, Y, Z. I tell you the vector at that point is that way based on the functional form of the electric field that we're going to derive. But this also has some kind of time dependence. It could be square wave. It's like this for a second, then it goes back to 0. Then it disappears. Then another second comes, and then third second it comes back. It could be any temporal dependence you want. In this class, what we're going to do is specialize to what's called time harmonic dependence, where things vary sinusoidally, which simplifies the mathematics tremendously. And we'll get to that. Here are the units and the description. E is the electric field intensity in volts per meter. So it's a distributed quantity, magnetic field intensity, amps per meter. We have the electric flux density in coulombs per meter squared. So this is a density, right? These are intensities. A density is some kind of quantity distributed over an area. So I can integrate it over a surface area and I can extract the units of coulombs, for example, or Webers, which are the magnetic charge equivalent. Then we have the electric current density in amps per meter squared and the electric charge density, which is in coulombs per meter cubed. All right. Okay, so to derive the mathematical functional form of divergence and curl in any coordinate system, we have to understand how to take the Taylor series expansion of a vector field. So I'm sure you guys have seen Taylor series expansions before. In this example down here, this is a 1D, a function of one variable. What are we doing here? We're taking e to the x, this black curve, or blue, I guess. And what we're trying to do is represent that in terms of a summation of simpler functions, which is something that happens a lot in engineering and mathematics. And if we have some function that there's only a handful of classical functions that you can use, that you can write down on a piece of paper. If that function doesn't fit any of those, then you have to start combining them in some kind of weighted combination way so that you can approximate a given function. Of course, e to the x we have, right? But if this was some arbitrary function, then I wouldn't be able to write down a closed form expression, right? But I could expand it in terms of simpler functions that I can write down, weighted by some coefficient. Add them all up, I can approximate the function. That's what Taylor series are trying to do. So I have some function e to the x. I expand it in terms of a summation of this functional form, right? So x to the n divided by n factorial. And you can see as we add terms, we get closer and closer to that expression. So that you've seen before for sure, undoubtedly. But how do we do that expansion for a vector field, right? So given this vector field f equal to, or f of x, y, and z, so now we're talking about spatially dependent vector fields only. That vector field has three components, right? On the left side, we have the vector notation. So here we have an f, an arrow above the f. This is the most powerful sign in all of mathematics. Equality means that if I have a vector on the left side, I must have a vector on the right. That will help you debug equations that you derive. Make sure you maintain equality in terms of the types of quantities, the dimensionality, dimensional analysis, and all kinds of things there. Here's a scalar function multiplied by unit vector in the x direction. So I want to construct this vector field f, right, at a given point x, y, and z. How do I do that? I evaluate this function's x component and its y component and its z component. These are functions themselves. If I give you this x, y, z, that fx function is different than if I evaluate it here. Then I weight that by a unit vector x, right? So I build up this vector field f at a given point x, y, z by evaluating its three scalar component functions. All right? I want to expand that vector field about the point x naught, y naught, z naught using a Taylor series. The way I do that is this following form, which is directly analogous, except we increase the dimensionality. F at a position vector r is nothing but a short notation for x, y, and z, is equal to, so this is about that point, near that point, at x, y, z is near that point, is the vector field evaluated at the point that we're expanding about, plus this matrix called a Jacobian matrix, which contains all the derivatives of the vector field. The Jacobian matrix operating on the vector field at that point, multiplied by r minus r naught. It should look very familiar, right? As a regular Taylor series, plus higher order terms we're not going to worry about. Okay, so if you write it out in matrix form, what do you have? You have fx, fy, fz. These are the components of f. So this is the vector field about that point is equal to, should be approximate, fx, y, and z at the point. So we evaluate the vector field at the point x naught, y naught, z naught. We add this Jacobian matrix, which takes all the derivatives of the components and all possible derivatives, right? First derivatives. And then we have this vector, which is displacement with respect to the point of expansion. All right, great. So, for example, this is something we're going to need to do the derivation in the next slides. If we want the y component of the vector field at z naught plus delta z, away from x naught, y naught, z naught, given the function, given the value at x naught, y naught, z naught, then we evaluate it like this. The y component at r is approximately the y component at r naught, plus to differentiate that vector or the scalar field component f of y with respect to z multiplied by delta z. What is the derivative? It's rise over run, right? So if I have rise over run multiplied by a run, I get a rise. So it's the value at that point plus its a rise at a different point, right? It's a slope. So if I multiply a slope by a displacement, I get the change in the function. And add that change in the function to the value at its original point, I get the value of, yes?
Is there about convergence balance? Is the series?
You mean the region of convergence? Not right now. Yeah, but that matters when you say how far can I push this approximation, right? How far away from x naught, y naught, z naught is it convergent? But yeah, don't worry about that right now. We're going to be doing everything very, very close to the point itself. As a matter of fact, let's look at that. The divergence. Okay, the definition, the terminology should be, 1 second, I just want to remember. This course goes till 9:30 to 10:45. All right, we're doing well, great. All right, fun. So let me know if I need to slow down though, right? The beginning should be something, but it's gonna get a little more difficult. So the vector field, so the nomenclature makes sense. Diverge, what does it mean to diverge? Things flow away from you, they diverge, right? Or converge, which is the opposite of diverge, means things are coming into a point, right? So for example, here's like a sink and there's water converging to the drain, right? So this vector field has what you can call negative divergence, or otherwise known as convergence, right? So the vector field is said to diverge. It flows outward from points of positive divergence. These are sources of a vector field, right? If you have a spout pouring into a bathtub, then that spout is a source of the vector field, right? It's diverging from the point where water is entering the tub. And then a sink is obviously the drain, right? Okay, so let's derive what we mean here. So we have a vector field A, right? Here's the vector, this is the point P. This point P is where I am evaluating sort of the functional form of the divergence. At this point P, I define a vector A, right? This is the vector A. It looks like it points into that point, but really it's the vector field A at that point, right? It doesn't have to point in. There's some vector associated with point P that you can find from the vector field A. Okay, we only know A at that point, right? That's the whole point of using the Taylor series expansion. We only need A at this point P because we're evaluating the divergence at point P. The other thing is, okay, so yeah, we only know the vector field at point P, the vector field A, right? We're going to construct a box around that point, and we're going to use the Taylor series expansion of vector fields to evaluate this vector field A at other points displaced, with delta x, delta y, and delta z. So that was the whole point of understanding how we take the Taylor series expansion of vector fields. So the one thing that you should remember, don't try to remember these formula, all right? They're in the back of a book if you ever need it during your research, but don't try to remember this. I'm going to teach you also a very general form. So you learn one in generalized coordinates, and you can specialize it to any coordinate system that you want. But rather than even memorizing that, the one thing you want to understand is this, the definition. What is the definition of divergence? This quantity here, divergence of A, is equal to the limit as delta V goes to 0, closed surface integral of A dot ds divided by delta V. That is all you need to know to derive everything else, right? Memorizing this is not useful, but memorizing this is. So what is it telling us? It's telling us that we have to calculate a closed surface integral of A dot with ds. So when we have this loop around the integral sign, it means closed surface. It means I need to integrate all sides of a closed volume. Our closed volume we're going to choose in this coordinate system is this rectangular or cube, right? It's a cube here. It has sides delta z or delta x, delta y, and delta z. All right? So we need to calculate this integral. The limit process is just to tell you that we want to calculate this closed surface integral as that cube shrinks down to a point. We want to find the flux out of a point, right? Say I have a little flashlight or lightning bug. I guess you have those out here, right? Lightning bug. And you have a box that you put around that lightning bug, right? The light is going to come out of the box. We want to calculate how much light is that, right? And we can do that. That's easily done if we knew the vector field A. But really, I want to associate that divergence with a point, the point P. So what I need to do is allow that box to shrink as close as I can to the point, right? So that's the whole point of the limiting operation. How do we calculate a closed surface integral? Well, we're going to break this one. So this integral here, So let's say this integral here becomes, we have to integrate over face 1 of the box, a dotted with ds1, right? Plus the integration over face 2, a dotted with ds2, plus dot, 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 the integral over face 6, a dotted with ds6, right? So the closed surface integral breaks into 6 integrations about planar faces, right? Of the vector field A dotted with ds1. What is ds1? It's the differential surface area on the face 1 and the normal vector outward normal associated with face 1. So this is what this looks like for the left face. Let's calculate that. The left face, we have A dotted with ds. So, okay, let me write it out. So this integral here, the integral over the left face, which we're calling, okay, that's the right face. So it's the back, right? I've denoted the front face here, which I should have probably said front, but this is the front face. So the back face is back here, right? The one you can't see. So that face has, let's see, this surface back here. So the surface back there has delta y, delta z, right? Delta y, delta z. The normal vector is in the negative x direction, right? So this is ds1, for example. All right? Very nice. That's the hardest part of the problem. Once you figure that out, everything's easy, right? Then you just go back to first calculus. So first year calculus. You have to figure out what this ds vector is pointing that direction. Now, if I take the dot product of A with that, so A dotted with ds1 is equal to this full A, so ax, ay, y hat, z hat, dotted with negative x hat, delta z, delta y. Then because of the way the dot product works, I only pick out the x component of the vector field A, right? So we end up here. Negative comes from the negative on the unit vector, the unit vector outward normal. Ax, because the x component is the only one that survives after the dot product, delta y, delta z, right? Okay, so what's the assumption I made when I made this equality? This vector field is constant over this surface ds. This box is assumed to be differential, right? Very small box. So in that sense, you can say that the vector field does not change over the back face of that box, right? The box is very, very small. Okay, so yeah, that's the left face contribution, right? Now we just have to repeat for all the other 6 faces. So here's the right face. Now here's where we have to use the Taylor series expansion. Back here, we had the vector field already at that point P, which is, since it's the same on all, that whole back face, right? Here's the back face, my hand. I know the vector field at that point P, which is the lowest coordinates. P always is the lowest coordinates, X, Y, and Z. So it's the lower coordinate box, corner of that box. The vector field's the same across all of this face. So I can factor it out. But here, I need to now evaluate what the vector field is here on this face, but I only know the vector field on the back face. So what I'm going to do is use the Taylor series expansion, right? So now we'll understand that. The right face, A dotted with ds. So let's write ds here first. This is, now it is still delta y, delta z, but now it's x hat, right? Because the outward normal, this outward normal here, n hat is in the x hat, is in the x direction. Okay, good. So we need to evaluate this vector field ax at x plus delta x, because at this point, we are at x plus delta x, right? And we want to know what the vector field is. We assume it's a constant all over that whole face. But we need to know what it is there. So how do we do that? Well, we use the Taylor series expansion. What is ax at x plus delta x? We learned in the last slide that that's nothing but ax at x, which is this back point here, P, plus the rate of change of the x component of the vector field A with respect to x, because we're displacing along x, multiplied by delta x, yeah? Very nice. Then we have delta y, delta z. So let's add those pair of faces. We get this, left face plus right face, partial ax, delta x, delta y, delta z. Very nice. Any questions on how we got there? Good, very nice. All right, same thing for the other pairs now. Pair them up, front and back, top and bottom, left and right. If you do all that, you're going to get similar terms in this. Partial AY with respect to Y, here it is. And then it has the same delta X, delta Y, delta Z. Then we have partial AZ with respect to Z, same delta Y, delta X, delta Z. So what do we do next? We now have calculated this part of our definition, right? We've calculated the closed surface integral of A dot ds. Now we have to divide by delta V and take the limit as delta V goes to 0. What does dividing by delta V mean? Divides by delta X, delta Y, delta Z, because delta V represents the volume. You're left with this classical formula you've seen before, right? So we derived it. So that's the divergence of A in rectangular coordinates, right? So you learned the mathematical form, you saw the derivation, still you might not get a tangible feel. What does it mean physically, right? What does it mean? So let's take a look at some intuition for I don't know why I can't get the slide to change here. All right. Let me see if I can go to it like this. All right. Okay, so what does it mean intuitively? What is the divergence, right? So let's see. So I like this slide because this is how I understand it, right? So the divergence of A, the definition is there. And then we calculated this definition by expanding the closed surface integral into its 6 phase contributions. Here we have 3 cases, right? Case 1, a flux line. So what are we trying to do? We're trying to calculate the net flux exiting or entering through a point. The net flux through a box surrounding a point, right? So here I have some flux. Here's my point, my box surrounding a point, delta X, delta Y, delta Z. Here's a normal vector N1 from the front face, N2 from the side face, all right? So I have some flux line coming into the box. It penetrates face 1, and it goes through the volume and exits the volume through face 2, right? So what am I doing when I'm doing this closed surface integral of A dotted with ds? What I'm doing is I'm doing accounting. I'm adding up, keeping track of the flux that entered the box and the total flux that exited the box. I want to find the net flux, right? So this flux line, it came in and it exited. So I would assume that, you know, intuitively that I would not get any contribution to the closed surface integral from that. And that's true. The reason why is whenever a flux line enters the volume, right? Remember the outward normals to this cubical volume are always outward, right? Whenever a flux line enters the volume, then it is oppositely directed to the outward normal. So this outward normal and the vector field that's going into that face, anytime it goes into the volume, have opposite signs, right? So you get a negative contribution from a flux line entering the volume because A dotted with A is this way, ds is anti-parallel. So you get a negative contribution. So it gives a negative contribution. Okay, this case. So this one, right? A dotted with N1 is the negative one, right? Now, whenever that same flux line exits the volume, then I have whenever a ray or a flux line exits the volume, it's in the same direction. It's parallel, you know, part is parallel. You have to take the dot product. But it's in the same direction as N2, right? The outward normal. So that becomes a positive contribution. And the way this works is these two cancel out, right? When it comes in, it's a negative contribution. That same flux line leaves, it is a positive contribution. You get nothing. Okay, great. So when I tell you what divergence means, if I take the divergence of a vector field, I'm finding all points of that vector field which represent sources or sinks. What points, X, Y, and Z, do I have a source of the vector field? What points do I have a sink of the vector field, right? So we'll relate that to Maxwell's equations in a minute. But if there was a source of vector field in here, a source of flux, then it would look like this one, a flux exiting the box, right? There's a lightning bug in there, and there's light leaving the box that doesn't have a paired coming into the box, right? So this one, there's a source inside because the contribution, if I calculate the divergence of A, it's greater than 0, means it's a source, right? There are flux lines that exit here, and there are not ones that cancel it that go in. Conversely, if a flux line enters the box but doesn't exit, then there was a sink of the vector field there. This flux line disappears in the volume, So it must have a sink, right? So the divergence calculated is negative. So when I calculate the divergence of a vector field, I'm locating all points of which are sources or sinks of that vector field. And what does Maxwell's equation say? My gosh. Maxwell's equations say that the divergence of, say, D is equal to rho. So what is the source of the electric flux density vector field? It's points of charge, right? It tells you. That's what Maxwell's equation tells you. It tells you that if I had to calculate what is the source of the flux lines of D, it's charge rho, right? So now I kind of understand what is the divergence. I understand what the divergence of a vector field is. The vector field D, if I take the divergence of it, it'll tell me the locations of sources or sinks of that vector field. And Maxwell tells me that those sources or sinks of the vector field D are points of charge density. So if I have a charge anywhere, then I know that it's a source, right? And it's going to start fluxing electric flux density vectors, right? Good? Cool. Very nice. Okay, good. Let's do an example, numerical example, yeah? So given A, the vector field A, e to the minus 2y x hat sine of 2x plus y hat cosine of 2x. I want to calculate the divergence. So I have some vector field here. Remember, there are scalar functions which tell me how the x component varies. There are scalar functions which tell me how the y component varies. I piece those two together and I get the vector field A at any point. So this is the functional form of a vector field. If I give you x, y, then you tell me exactly what vector is there, right? You can do that for every vector, or every point rather. So you calculate divergence of A. So here we have, okay, just checking if anyone online has questions with the chat thing. So let me make sure. Okay, good. So the divergence of A, we calculated. Here's our formula we derived before, right? We have partial by partial x, partial by partial y, partial by partial y, or z. And then I just take the dot product of this sort of del vector, which I don't want you to start thinking of it that way yet. But it's like this, right? You take the dot product of some vector with your vector field, A. Anyhow, if you carry out this computation, you get this following form, and that comes out to 0. What does that mean? What does it tell you? What? Where are they? So this divergence calculation came out to 0. What does that mean for that vector field? It means a lot of things, really, but one thing, anybody? Exactly. There's no sources or sinks of that vector field, right? There's no places where it converges, no places where it diverges. It's just a vector field that permeates space, right? Good. Of course, it also tells you, if you remember vector calculus, that it's purely a solenoidal vector field. It has curl, but it does not have divergence. And in that sense, it's a non-conservative vector field, but we'll get to those definitions. So if this animation works, so sorry, let me see. Why is this? There we go. Okay. Okay, it's cheesy animation, but what am I doing? I'm moving that box all around different points in space, and I'm trying to calculate the closed surface integral. I will always get a null result, no matter where I move this box throughout space, right? So every location I can test, which I don't need to do that brute force. If you're doing it numerically, maybe you have like an array of numbers, then you might have to do that on a computer, right? You might have to move a box around and calculate the closed surface integral because you don't have a functional form of A. You just have an array of numbers on a computer. But I've done all of that in closed form like this by just calculating the divergence of A. So no matter where I put that box, net flux is 0. How about this result? Given A equal to rho hat rho cosine phi, phi hat rho sine phi, z hat 3z. Calculate the divergence of A at this given point now, right? So here is the form of the divergence operation in cylindrical coordinates. You will not need to, okay, so it's good to know that. Even after doing research in this area for a long, long time, half my life or more, I don't remember this exactly. I mean, I probably could write down, but to be honest, I will go to the book, make sure I didn't write down wrong, and look in the back flap. What I want you to memorize is the concepts behind it, the intuition, right? The geometric meaning is so much more important than to memorize this formula. But I sound like I'm telling you not to memorize it, but if you can, memorize it. But the thing is, the formula is there, all right? And we'll calculate the divergence of A. So here's the divergence of A. You calculate all of this result here, you get 3 cosine phi plus 3, right? Now we have to evaluate this function as a function of phi at this point, 2, 0, 3. And we know that this is rho phi and c. So phi is equal to 0. So we get a result of 6. At that point, the vector field has a divergence of 6. All right. So that means it's a source at that point, right? The interesting thing about this vector field is because this vector field grows with rho. All right. What does it mean for a vector field to grow with rho, right? If I'm at this rho, then I have, okay, so here's a box, right? I'm on the front face, rho is equal to 1, for example. That vector field has a direction, the vector has a direction and an amplitude, right? At that point. But the vector field is growing with distance. So by the time I get to the back face, I have more flux than I had at the input face, right? So I'm always gonna have divergence in this vector field because here's the box. This vector here entering, the box is weaker than the vector exiting the box, right? Even if it was a constant vector field, not with the cylindrical radial symmetry, if it was a constant vector field, but it grew with z, then the vectors entering the box are weaker than those exiting. You can never cancel them out, right? You have more leaving the box always than you have entering in the z direction. So you'll have a divergence, right? Okay, good. Any questions?
It's not really like a conical shell or you have the spherical shells. And it just keeps having more field.
Yeah, exactly. For every radius and row that I go to, the next row has more vector field. The vector field's growing with rho, right? It's proportional to rho. This is kind of obvious, right? It's radial leaving some point. Obviously, there's a source somewhere, right? But I just want you to kind of get the idea that, that previous idea where one flux line going in, one flux line going out, it's good to have that intuition, right? Geometry. But if the flux line going in is weaker than the one coming out, then when you do that dot product, you get more results coming out than going in. So you got to be cognizant of these other things, right? Good. Okay. So let's see. Let's do the curl. All right. 2 properties that a vector field has that uniquely describe it, and we'll see that later, is its divergence and curl. If you specify the divergence and the curl of a vector field, then that vector field is uniquely described. So it's kind of like the bases of a vector field, right? You can always expand a vector field into its divergence and curl, and you have the full description. So what does a curl mean? The curl of a vector field at a point P measures the tendency of particles at P to rotate about the axis that points in the direction of the curl at P. So that's a lot, right? Let's unpack it. So we have, there's a word, direction of the curl at P is an axis. So here, if I have this drain, and if the water is swirling about the drain as it enters, then obviously it's swirling about an axis, right? So here's a vector field. The water is swirling about an axis, right? So how do we measure curl? Well, we first have to define an axis about which we're talking about the swirling of, and we have to define how fast it's swirling or how much it's swirling about that axis, right? Now, because I have to define an axis, I can uniquely describe that vector in terms of its 3 components. I define the x-axis, I find out how much it's swirling around that. The y-axis, how much it's swirling around that. The z-axis, how much swirling about that. I add those 3 components together. I find the direction of the curl as I add up the components, right? So the difference between the divergence and the curl is this is going to result in a vector. Remember, these are operators. So this curl of without the a, right? Just the curl of part. That is an operator. It means nothing by itself. It's like taking a matrix A and multiplying it by x to get b. Well, if I just consider a by itself, linear transformation, it doesn't mean anything on its own. You have to operate on another vector to produce a new one. That's what this curl operator is. It's an operator. I operate on a vector field, I get some results. In this case, the operation of curl on a vector field gives me a new vector field called the curl of A. Before I had divergence, which is the del dot. If I operate on a vector field with del dot, I get a new vector field, but it's, or not a vector field, I get a new scalar field, right? It's not a vector field, it's a scalar field. Okay, so let's do the calculation. So here's the definition, the most important thing. The definition of the curl of A is the curl of A dotted with n hat. So what is n hat? Is the axis about which I want to calculate the curl, the circulation, right? So assume it's n hat here. And I want to calculate how much does the vector field rotate about the axis n hat? Well, I take the limiting, I take the limit as delta s approaches 0, but now delta s is a plane orthogonal to the vector n. I want to find out how much the vector field rotates or circulates in that plane orthogonal to the axis n. And how do I do that? Well, I have to calculate the closed loop integral now of A dotted with dl, right? And we'll get some intuition for this as well. So what is the closed loop integral? We have this, A dotted with dl. Let's say we're looking at some path in the xy plane, for example. Then this breaks into 4 line integrals. Line 1, A dotted with dl1, plus line 2, A dotted with dl2, plus plus line 4, A dotted with dl4, right? And what am I doing? I'm taking the dot product of A with that. Let's do the calculation. I think it'll be a lot better. So here's an example, right? We have this geometry shown in the lower left. I have this point P, right? I know the vector field at point P. Oh, actually not at point P, at the lowest coordinates. I know it here, right? But we're assuming that this is so small that it's the same value all throughout that face. I want to calculate the curl of A dotted with X, right? So here's the normal vector. How much does A circulate about the X axis, right? Okay, so what do I want to do? I have the vector field A at this point. I have a path here. So, excuse me. I have a path here from 1 to 2, from 2 to 3, from 3 to 4, and from 4 back to 1. Okay. I want to calculate the closed loop integral. What am I doing? When I take the dot product with the first path, which is from point 1 to 2, I'm saying, does vector field A, which is everywhere, does that vector field have an X component? So I have an X hat unit vector in my arm, and I have a vector field A. If it's orthogonal to that path, then it doesn't have any component in that direction. If I take the dot product of A with the unit vector X hat, well, in this case, path 1 to 2 is Y hat. Then I want to find out how much of that vector field is in the Y direction along that path, yeah? So the way I set this up is the unit vector from 1 to 2 is directed along the Y axis. Then from 2 to 3, it's directed along the Z axis. Then from 3 to 4, directed along the negative Y axis. And from 4 to 1 along the negative Z axis. So I'm actually trying to calculate the circulation of that integral or vector field, right? Because I want to take the dot product of the vector field A with this path, then that path, and that path, and that path. My path is a circle. If I take the dot product of vector field A with that circle, if that's a non-zero result, then the vector field had some circulation around that path. I'm dot producting it with that path, right? Okay, let's do it. So here, look. The integral, the closed loop integral is from 1 to 2, 2 to 3, 3 to 4, and 4 to 1. And that is the first one, from 1 to 2. What is DL along that path? So DL1 to 2, right? That is going to be Y hat, right? Delta Y, right? Okay, now I take the dot product of A with that DL1 comma 2, and that says, does vector field A have any contribution along this path in the Y direction, right? Okay, so that's AY delta Y, because remember A is AX, X hat, a y, y hat plus a z, z hat. Taking the dot product of a with dl gives, and dl has only a y component, then I'm only going to pick out the y component, right? So ay delta y. Now, from 2 to 3 requires me to evaluate the vector field at this point, at point 2, or anywhere on the face, right? Over here on this side of it. Anywhere along the path 2 to 3, given the vector field only at the point 1. We need we need the Taylor series expansion, right? So that's what this is. This path, this one here, is z hat delta z. That's dl 2 to 3. So when I take the dot product of a, I should only get a z, but I need a z plus delta y, right? Okay, so that's not the right way to write that. It should be written like this: a of, say, x, and then y, and then z plus delta. No. Sorry. Once again, should be y plus delta y, right? Y plus delta y, and then z. Okay, so how do we find that? Well, it's right here. Change this back to red. Yeah. A z, the value of the vector field at the point we know, plus the rise over run in the y direction, because we want y plus delta y multiplied by delta y, and then the delta z comes from the path integral dl vector. Yeah? Very good, very good. All right, same thing for the other two paths. We add those up, and what do we get? This tells me how much that vector field rotates about the x-axis along this path, right? If you wanted to know, let's see how I can think of this. We're gonna do this later in a couple slides. I have some vector fields in this room, right? I want to add up that vector field along some path. When I go from here up to like here, right? I want to add up that vector field. It means I need to integrate that vector field along my path. And the way I do that is I take the dot product of my vector field with my path vector everywhere I go, and I add it up, right? We'll see that. Let me table that, and you're going to see it in a slide from here. But makes this kind of make more sense. I want to add up the vector field around some circular path. If it's non-zero, then it's rotating. It has a non-zero net contribution around that path, right? What if it's negative? It's going the other way, counterclockwise, right? Or clockwise. What if it's 0? If it's 0, then let's say the vector field is constant in the y direction. Then from path 1 to 2, I got a positive contribution, right? Because A is in the same direction as DL from path 1 to 2. 2 to 3 is orthogonal because the vector field is only in the y direction, and the path from 2 to 3 is z hat. Same with the path from 4 to 1, z hat, orthogonal, 0. The dot product gives 0. The path from 3 to 4 is exactly the opposite to the path from 1 to 2. Negative y hat multiplied by a constant unit or constant vector field in the y direction. So it gives you 0. Constant vector field does not rotate, right? Okay, so you do the same thing for the other components, and you divide by the area, which is delta S, right? So delta Y, delta Z for the X component, and then you have delta X, delta Y for the Z component, and delta X, delta Z for the Y component. You divide all of those by the definition, you get this for the curl, okay? All right, so you've probably seen this before. This doesn't tell you anything geometrically. This definition over here does. It tells you that the vector field is circulating. I'm calculating the circulation. You'll get the idea of how taking the dot product of a path unit vector with a vector field adds up to contribution. As soon as you get that idea in your head, all of this is super intuitive. All right, and we'll try to get that going. So here, look, there's some vector. Okay, so the other classical way to describe this is you have these paddle wheels, right? Here's some crazy vector field in the XY plane, and here are some paddle wheels that I imagine this being water on the surface of like a lake or something. You drop these paddle wheels in here, so they all have normal vectors, which are z hat. So I'm calculating the z hat component of the curl vector using this kind of cartoon here. If they're rotating fast, then that means that the vector field is rotating a lot about that point, right? If they're rotating slow, then they're not rotating much. And then if they're not rotating at all, this one's rotating very slow. So that's kind of a geometric picture of what's going on with the curl. So you can calculate it. Okay, this is a warning, Cartesian coordinates only. You can use this determinant expansion of this matrix here, which is what I always do. But there's a way we're going to learn a similar formula in generalized coordinates that allows you to do it for all the coordinate systems. All right? Good. Any questions? Yeah.
I don't know if this question makes sense, but is there like a reason why that like using that determinant formula is true, or is it like coincidence basically?
Well, what you can do is you can write this more compactly in this form. So if you look at this, someone smart that looked at this saw it, right?
Well, like I understand mathematically that they're equivalent, but like, I don't know, is there some way that you know that without mathematically just showing that equivalence, I guess?
Yeah, maybe, because what does the determinant calculate? The determinant calculates the scale factor associated with the linear transformation. So there might be a way to relate that. That's a question I haven't thought about, and I don't feel prepared to give you an answer about. I know what the geometric meaning of a determinant is. It tells you if a linear transformation has full rank or if it collapses some of the rank and goes to null space or whatever. It has a geometric interpretation. How it fits in this context, I'm not sure. I'd have to think about it, but there must be, right? There must be, yeah. But that's great that you're thinking about these things, because that's what you want to try to do. You want to try to look at something and not see it for face value. Add information to it, right? Try to add a geometric picture to it. All of these expressions here tell you something about physical reality. And as soon as you read words on a paper, right? In a book, these become images in your mind. So you read a book and you're playing a movie in your mind. You should get that way with this language. You have to work, you've been reading English language your whole life, right? But once you're able to read this new language that you're learning and it becomes pictures, then that's when you become very, very proficient, intuitive. You can start doing a lot of interesting things. So try to do exactly what you're doing. What is the geometric picture of this, right? What is the picture associated with this mathematics? Very good. Yeah, I will think about it though, and I'll let you know if I come up with anything. Good question. Any other questions?
Yes, just the determinants like the parallel pipette of the basis. So when you're integrating along the vectors, you're kind of making a volume.
Yeah, it's definitely associated with the volume. That's true. The determinant is associated with the volume. But how does that represent circulating vector fields? We got to think about it. All right, good. So let's do an example for this one as well. So we're given a vector field F, x hat ln 5 plus x squared cosine pi x plus y minus y hat ln of 2 plus y squared and so forth, right? That's this vector field here in blue, all right? So that vector field in blue on the screen is given by this vector field F. It's in the xy plane only. We want to calculate the curl. So what we're going to do is use the minor expansion of this determinant, or expansion by minors, and we get x hat. The first term, if you cancel out the first column and the first row, partial by partial y of 0 gives you 0, minus partial by partial z of fy, right? Then we have a minus sign because we alternate as we go across with the minors. Y, you cancel the middle column and the first row, and you calculate this result and do the same thing for z, yeah? Okay, if you then calculate these derivatives and string them together, you get the following result for the curl. All right, so that vector field, this curl of F is the vector field that's plotted to the right, not F, I'm sorry. No. Apologize. The vector field F is in blue. Yes, the vector field F is in blue, and then we have a select number of vectors in green that are plotting the curl of F, right? So at each of these paddle wheel locations, we draw the green arrows. The green arrows are the vector field, the curl of F at those points. And you can see the magnitude depends on how fast it's curling, the direction, whether it's up or down, depends on whether it's clockwise or counterclockwise. And those are some representative values, right? Okay, you can go through this example too when you go back through the slides and review. Okay, gradient. So we have to get through this mathematical introduction and the Maxwell before we get to super fun stuff next lecture. So bear with all of this if you've seen it. But the gradient of a scalar field. So we took the gradient of a scalar field, right? We convert it into a vector field, or we represent that scalar field rate of change as a vector field. Is a vector field whose magnitude is the rate of change at which points in the direction, at which points in the direction of the greatest rate of increase of the scalar field. So this one's easy to understand, right? If you have a mountain and you want to climb the fastest up that mountain, then you want to go in the direction of the steepest descent, right? That's the direction of the gradient. So how can we formalize that mathematically? So let's say we have a vector field R here, or a vector, position vector R, which points to this vector field M, which has this vector here. We have R plus dr now points to a new vector N, right? So dr is the path that goes from, this is how you describe dr in general, dx x hat, dy y hat, dz z hat. Now dv, which is the change in the scalar field, is the total derivative. I want the total change in v along that path, dx, right? So what is that? The change in the voltage, or v, with respect to x, rise over run in the x direction, multiplied by a change in x. Plus, I want the contribution to the change in v with respect to the y displacement, multiplied by y, plus the same thing for the z. Right? I add up all the contributions to the change in v. Now, if I look at this expression, I can say that, well, I can write this as the dot product of my dr vector, which is dx, dy, and dz. I call that dr. And then I have this new contribution, whatever's left over, I'm going to call the gradient of v. All right? So the gradient of v is obviously partial v partial x, x hat, partial v, partial y, y hat, and so forth, right? Okay, what does this tell us? This expression. It tells us that if our path, remember the definition of a dot product. If I have two vectors that are orthogonal and I take the dot product, I get a result of 0. So if my path that I'm trying to evaluate the change in the voltage or change in the scalar field v is orthogonal to the gradient, then the vector field, or sorry, the scalar field doesn't change, right? So that means you can define what are called equicontours. Let's say v is voltage. They're equipotential contours for all values of path dr, of which this result becomes 0. Or on a mountain, if my path is around what's called an iso incline, or I forget what they call this. Iso, this is the same height, right? So if I go along that path, dr, and I'm not changing the height that I am at the mountain, then that path is that gives you a dot product of 0. So what does that also tell you? That tells you that, how do you maximize a dot product? dr needs to be in the same direction as the gradient of v. Then I get the most change, right, in v. This dot product is maximized. So that means that the gradient points in the direction of maximum rate of increase. So here's a vector field, or a scalar field rather, f of x and y, minus cosine squared x plus cosine squared y, and then I square that whole thing. That's depicted, that's this orange surface. If I take the gradient of that scalar field, then I get this blue vector field, which is below it, right? So what does that mean? It means that you can kind of see it. The gradient always points in the direction of maximum increase. So if I'm at the bottom here at the center of this coordinate system, at the origin, if I want to go fastest up this orange surface, I have to go in the direction of these blue arrows, right? Okay, great. Any questions? What time is it? All right, so looks like we have to end here. But so what I want to say is we got to get through this introductory material. We're going to get to some super exciting stuff this semester. You guys are going to become experts in electromagnetic theory and materials engineering. I'm going to try to sprinkle that all throughout. And you're really going to understand how electromagnetic fields interact with matter and how we utilize them for communications, antennas, radiation, and things that underline your entire discipline. Whether you're doing circuits or computer engineering or whatever, this is all super useful, all right? So I hope to see you guys throughout the semester and even in the next course. Thank you. If you have any questions, let me know. Email me. I'm available. You can knock on my office door anytime you want. You don't have to have an appointment. Just come interrupt me, and we can have a discussion on anything you're thinking, all right? All right, see you guys. How's it going? Yeah, I can do that. As a
Yeah, yeah.
okay, sure.
Yeah, so.
Send me an email so I have your unique ID or your Virginia Tech PID,
Okay,
and then I'll add you through that.
Okay,
Yeah.
yeah, thank you.
Okay, great.
Have a-
You too. How's it going?
It's going well, how are you?
Good, good.
Just want to introduce myself.
Yeah.
Sorry.
Jordan. Tristan?
Tristan.
Very good, very good.
I'm a physics student transitioning to an electrical engineering program.
Nice. Welcome. Well, that's good.
So, very excited.
It's gonna be fun. We're gonna do a lot of really cool stuff once we get past, you know, the introductory, get us all on the same page stuff. It's gonna be fun.
I think regarding the determinant question,
Uh-huh.
maybe have to do with index notation. I remember maybe for index notation, I don't quite remember.
Oh, with the how it represents the determinant?
Right,
Yeah.
that's just a guess, I don't recall.
Yeah, that would be great. There must be some kind of connection there, right?
Right.
Because determinants have geometrical interpretation. And if it also represents the curl, I'm sure there's some way to link the two. Yeah, that'd be great. If you see anything, let me know.
Of course.
All right. Nice to
Thanks so
meet you
much.
too.
Have a good one.
You too.
Hi, Professor.
How's it going?
It's good, Tyler.
Jordan.
How do you pronounce your last name?
Voodoo or Badoo. Yeah.
Yeah, thanks for the lecture. I was wondering about this one.
Yeah.
So you said if the flux goes in this face, let's say it's normal to face one,
Uh-huh.
and then the same flux leaves face two, but it's at an angle,
Yes.
then you have less product on this side.
That's
So
it.
wouldn't that mean you have a net flux? I mean,
That's a great question. But so if it exits an angle, then it'll have a dot product with face N2. But then the rest of it's gonna be dot product with the back face N3, right? So you'll split that. So let's say this ray is coming in perfectly parallel to N1.
Yeah.
Then you'll have a negative contribution to the whole ray.
Right.
When it exits, let's say it exits that back corner.
Okay.
Then that exiting ray will be split into N2 and into N3, right?
and if it leaves here,
Yeah,
so what if it leaves here? I guess it doesn't matter, it's arbitrary.
yeah, so the vector field's constant everywhere, right?
Yeah.
So if it exits here.
Oh, it's constant, okay, that's what I was saying.
Yeah.
Because
It's
we
supposed to
have
not vary over that
a
surface.
Sufficiently small volume that it should be constant.
Exactly.
Okay. Thank you.
Yeah. Cool. Yeah, let's go. Yeah.